When classical mechanics calculates angular momentum, it relies on this visual model, a mass orbiting a center point at a specific distance. The formula is strict, position crossed with momentum. But applying this spatial model to an electron immediately breaks down. An electron is a point particle. It lacks physical volume. A radius of 0 dictates that its physical angular momentum must be 0. Yet experimental evidence shows that electrons possess an intrinsic, measurable magnetic moment. They carry an angular momentum that does not come from moving through space. To resolve this, quantum mechanics discards spatial coordinates entirely. In the quantum regime, true angular momentum is not a description of physical geometry. It is a strict, self-contained set of algebraic rules. We are going to derive the rules of intrinsic spin strictly from abstract commutators.
We map those constraints into matrices. Watch how those matrices rotate space. Drop them into a magnetic field to predict the exact mechanisms that power modern imaging technology. Stepping away from three-dimensional space and trusting pure abstract algebra is the only way to accurately predict the behavior of elementary particles. This equation is the bedrock of all quantum angular momentum. It is the fundamental commutation relation. Jx, Jy, commutator, equals I h bar Jz. Everything about spin is built entirely from this single constraint. From this relation, we find two compatible observables, the total angular momentum squared, J squared, and its projection along the z-axis, Jz. Because they commute, they share simultaneous eigenstates, which we represent as the abstract vector ket Jm. The algebra also generates ladder operators, J plus and J minus. Applying the J plus operator to our state increases the z component of angular momentum, the m value, moving the state up by exactly 1 unit of h bar. But the system has finite total angular momentum. This ladder cannot climb infinitely. There must be a maximum ceiling where applying J plus yields 0, setting a top rung at m equals j. Likewise, there is a minimum floor where m equals negative j. Because the ladder steps strictly in integer units of h bar from negative j to positive j, the total number of allowed states in this bounded sequence is exactly 2j plus 1. For the ladder to connect precisely from bottom to top using integer steps, the distance between them, 2j, must be an integer. This mathematical limit forces the quantum number j to be either a whole integer, which describes orbital mechanics, or a half-integer. Classical physics could never predict a half-integer state. The abstract algebra of the commutator requires the existence of half-integer intrinsic spin. To calculate actual experimental values, we translate these abstract operators into matrices. A quantum system containing 2j plus 1 states requires a square matrix of that exact dimension. For an electron, j equals 1/2. 2 times 1/2 plus 1 is 2. The abstract spin-up and spin-down kets morph into two-element column vectors, known as spinors. The operators acting on them must therefore be 2x2 matrices. We start by deriving the SZ matrix. Because our spinors are already the eigenvectors of SC, with eigenvalues of positive and negative h bar over 2, the resulting matrix is perfectly diagonal. The SX and SY matrices cannot be diagonal because they do not share these eigenvectors. We construct them by running our two spinors through the J plus and J minus ladder formulas we derived earlier. Extracting the shared h bar over 2 scalar from these arrays isolates the Pauli spin matrices. These three Hermitian matrices encode absolutely everything that can be known or computed about an electron's spin. If intrinsic spin does not describe a mass physically turning in space, why does physics retain the term angular momentum? The answer lies in the quantum mechanical concept of a generator. Just as the linear momentum operator acts as the mathematical generator for translating a state across physical distance, the angular momentum operator generates rotations. This visual represents the rotation operator, an exponential function containing the Jz matrix. Feeding an angle phi into this operator applies a rotation to the quantum state in a complex Hilbert space. The Pauli matrices are the mathematical engine dictating exactly how quantum states transform when an observer rotates their coordinate system in three-dimensional reality. To see this static algebra evolve over time, we introduce a physical interaction. We define the system's energy using the magnetic dipole Hamiltonian. H equals negative mu dot B. We place our electron into a strong, uniform magnetic field, designated B0, pointing strictly upward along the z-axis. When we insert this Hamiltonian into the time-dependent Schrödinger equation, the initial spinor state does not physically move. Instead, its components acquire complex phase factors that tick forward continuously as time advances. By calculating the expectation values of the spin components over time, we can visualize the probable state of the electron. Because the magnetic field aligns with the z-axis, the expectation value of Sz remains constant, but the values for Sx and Sy oscillate harmonically, tracing out a circle in the transverse plane. This accumulation of complex phase factors in the math manifests in physical reality as Larmor precession. The abstract quantum property sweeps around the magnetic axis identically to a classical gyroscope fighting gravity. If the spin simply precesses around the z-axis indefinitely, how do we force the electron to jump from a low-energy alignment to a high-energy anti-alignment? This split diagram illustrates the solution. We introduce a second, much weaker magnetic field, B1, along the x-axis, and we oscillate it. The graph on the right displays the probability of the electron absorbing energy and flipping its spin state. This probability curve only reaches 100% under a strict resonance condition. The frequency of our weak oscillating field must perfectly match the particle's natural Larmor precession frequency. When they lock in, the spin flips entirely. This controlled spin flipping is called Rabi flopping. It allowed researchers to precisely manipulate quantum states in early laboratories by sweeping radio frequencies until the atoms resonated. By scaling up this exact quantum control mechanism and applying magnetic field gradients to isolate specific spatial locations, physicists mapped the water density in human tissue. Paramagnetic resonance, the deliberate matching of driving frequencies to quantum spin precession, is the direct engineering bridge between abstract quantum matrices and modern diagnostic medicine. We started by discarding the physical orbit. We built an algebraic ladder out of strict commutators and locked those rules into 2x2 matrices. Those pure matrices generated spatial rotations, naturally evolved into Larmor precession, and accurately mapped the mechanics of resonance. Quantum mechanics achieves its highest predictive accuracy when we set aside spatial intuition and follow the strict mathematical consequences of the commutator.